Just so that
Is it just whatever?
you know, you can kind of see what I've done between lecture last week and lecture this week. I posted a couple of videos and also posted a video to chapter 15. Yeah, part two. Yeah. So, you know, that's pretty much what we covered. Or where's the video from last week? Was that? Yeah, that was 29. So this is what we did last week, and then from my office, I just took it all the way down through focus font size, I believe, is the last thing that I got to. So what we're going to do today is just kind of review what we did last week and just run through the PowerPoints in kind of a sprint to get to just past where I left off with this particular reporting. So I've been reporting just, you know, if I have 15, 20, 30 minutes of downtime, I've just been reporting and try to get them into the modules for you to have. So what we talked about last week was image quality, what image quality meant, and that was basically contrast and density and distortion, minimizing the distortion. So it was the ability to demonstrate accurately the size, shape, and representative contrast and density of a structure, right? So we talked about what we would talk about, which was distortion types, sharpness of the lines being your spatial resolution. We talked about how to differentiate between, on a test question, between spatial resolution and contrast resolution. That was always that if it just said resolution, what were we talking about? If it just said resolution, spatial resolution, right? So contrast resolution was always going to say contrast resolution or just contrast. Contrast equals contrast resolution. Resolution is spatial resolution, geometric factors, and all that, right? So we looked at some definitions. We looked at what spatial resolution was, and that was actual sharpness, and we talked about penumbra versus umbra. Umbra being a sharp image, penumbra being the fuzziness, right? Then we talked about contrast being black and white, the difference in densities between adjacent structures. So that's really kind of what you're going to be looking at is in contrast for questions that specify difference in density. That's your contrast, right? And or your contrast resolution. So we talked about sharpness for recorded detail being your resolution, sharpness, geometric factors, your actual lines, along with the absence of noise. So if you've got an image that is dominated specifically in this case by quantum model, you're going to have a lack of resolution. Contrast resolution, whenever we have a lot of scatter radiation, the scatter radiation, what we're going to lose is the ability to see that resolution, right? Fog. So we looked at that. That was a line pair per millimeter test tool. I wish I had a star test pattern to show you what it looks like. Star test pattern, I mentioned last week, has long been considered the most accurate of our resolution test tools. And I understand that now with the resolution test tools that are built into a system, this is really just focal spot. This is the only thing that this really tests anymore, or what we use to test anymore. You could test the resolving power of your image receptor systems with this as well, but they build that into the system now. So your resolution test tools for the system, and especially for display, are built into the system. So it's record and display spatial resolution. We talked about the CR imaging plates, and we talked about what causes a loss of spatial resolution. That was the size of the phosphors, a reflective layer created a loss of resolution. So in the CR imaging plates, how we got the best resolution was with small phosphors and a thin phosphor layer. Unfortunately, that came with a reduction in speed. So what that comes with is an increase in patient dose in order to get that exposure back to the image receptor. So the different things that had to demonstrate spatial resolution were the image receptors. The CR readers also had played a significant role in that. You remember we talked about the beam shaping optics, had to keep the size of the laser beam consistent between both ends of the image receptor. We had to have consistency in the time travel of the image receptor as the CR plate went through. It had to be consistent. That was your slow scan. Then you had the fast scan that was actually scanning the plate as it went through. So we've got CR readers factored into that, and then we've got image display, and that will be your matrix on your monitor. So we talked about how the plates worked. You make an exposure, and it holds on to some of that, and that's what we call the phosphorus being in a metastable state. They hold on to some of the energy that they absorb in the exposure. So that's your stored energy that's released during the read cycle. And that stored energy is going to be dependent on how much exposure it takes, regardless of whether it's kVp or mass. It just holds on to a portion of the energy. And what we get is an excitation of those outer shell electrons. They temporarily leave their shell, they drop back into place, and they glow a little bit, but they also hold on to some of that, and that's what we call metastability. So metastability, we defined that, and that was, where was that? Somewhere in all this. Anyway, metastability was just a higher level of stability. It didn't mean that it was more stable, it just meant that it was holding on to some energy, and it wasn't in its most stable state. So we talked about the sharpness again, smaller phosphors, better resolution, thinner phosphor layer, better resolution, and the reflective layer. Cut back on radiation exposure to the patient, but unfortunately that came with a loss of resolution as well. We talked about, again, resolution, and what had the highest resolution was direct exposure, followed by detailed screens, followed by fast speed screens. That may have been where we left off last week. Is that about where we ended?
We left off on the read side.
What's that?
The read side, the read side.
A little bit further than that? Okay. Okay, so just in screens, that's what we have, films and screens. Just a graphic representation of really how not only the screens work, but also how the CR plates work as well. Small phosphors, high resolution, large phosphors, because the light spreads out more, we get a loss of resolution. So a lot of similarities between the two. We talked about the fast scan being the pivoting of the laser as it's scanning the plate that's going through on the slow scan. So the slow scan is just the movement of the plate through the CR reader, as opposed to the read itself is actually happening during the fast scan, and that's where the laser pivots. And again, because the beam diverges, it has to be focused to keep the thickness or the width of the laser constant on both sides of the imaging plate, limiting that divergence of the beam to maintain our sharpness for reported detail. So thinner layer gives us the highest resolution. That's what we'll call interrogation. Interrogation is just the selection of each one of those phosphors to release its metastability, or as much as it can. The slow scan had to be consistent as well, but it also, both of them have to be mechanically sturdy, stable, so that you don't introduce some sort of motion artifact. Once in a while you run across an image, an X-ray image, where you've got these squiggly lines, you've got a nice, fine, bony cortex, and all of a sudden it just kind of goes, it's like it's got a P wave running through it. And that's exactly what happened, is that for whatever reason there was some vibration during either the fast scan or the slow scan. So the read cycle occurs at the exact same time as the laser scan, so the stimulation has to occur at the same time that it's detecting the light. and it feeds it into a photomultiplier tube to eventually become digitized and become your digital image. So at this point, it's all analog. Y'all know the difference between a latent image and a manifest image, right? Okay, so a manifest image being the image when?
As soon as you capture. How does the process one?
What's that?
Or is it the finished
Right
one?
after it's made.
Okay, the latent image is right after it's made, it's still on the plate. So in a DR exposure, your latent image only lasts that long. You know, it's the exposure to the plate and then it's immediately processed. In CR and film, the latent image exists until you run it through the scan or you run it through the processor. So the latent image is not the image that you see, it's the image that only the image receptor itself sees, right? The manifest image is what comes up onto your computer. So this is all creation of the manifest image from the latent image is what we're looking at here. So the read cycle occurs at exactly the same time as the laser scan. If you scan it and you wait a little while and then try to read it, it ain't gonna happen. You know, it's gotta detect the amount of light that's coming off each one of those phosphors in real time so that it can detect how much that phosphor glows so that it can feed it into the computer and give you some sort of representation of what the density was of the structure based on how much it glows. So the more dense the structure is, the more that structure absorbs and the less you get metastability and the phosphor is directly underneath that structure, right? So when you stimulate it, it doesn't glow as bright as, you know, the area under a lung is gonna glow a whole lot brighter than the area behind a rib. Does that make sense? So that in that way, we can make a differentiation between different tissue types. So it's fed into light collecting optics and then eventually into a photomultiplier tube, which does just what the word implies, it multiplies the photons. So, and this is pretty much where we left off, is that right? Okay. So again, these are in Canvas, so we're not gonna spend just a tremendous amount of time on them, but you know, just in case you have had an opportunity to look at the videos, and if you've got any kind of questions, then we'll, you know, address those. So digitization, not a word that rolls off my tongue real well, occurs conveniently enough at an analog to digital converter. Just like in fluoroscopy, you got an A to D converter. It takes that analog signal, everything is analog at this point, and it digitizes it. When it digitizes it, it gives it a numerical value based on the light that came off of that individual phosphor. So it's the process of taking that information off the plate is, and the interrogation is what we call sampling. So we sample the phosphors, measure the light that comes off as released, we quantize it, and give it a digital value so that in a digital world we can represent how much light that gave off, right? So again, back to the analogy of the comparison between the soft tissue, the lung tissue, and the ribs. Maybe it gives it a value of 50 for the lung tissue and a value of 20 for the ribs based on the glow that comes off that. Those are just numbers I'm pulling out of the air. So eraser is where, you know, even after you've got laser stimulation and the release of the light and the detection of the light, you still got some metastability going on. And the eraser bank is just a whole lot of fluorescent light bulbs that glow really, really bright to release as much of that as possible. And if you don't erase, if you don't have an eraser bank, then you process your image, you take your image receptor and you take it back up to the floor, you shoot another chest x-ray on it, and what you're gonna get is what looks like a double exposure, okay? Even though the first image has been lifted, it's still gonna look like an image, a double exposure on the image receptor. So it's got to be erased. right? So it runs through this bank of light bulbs, and they're just all fluorescent light bulbs, maybe a bank of 10 fluorescent light bulbs that put out a lot of light, and it releases the rest of the metastability so that you can reuse them without getting that ghost image, is what they call it. So if, over time you start having ghost images, and it doesn't really make sense why you're having ghost images, chances are what you've got are burnout light bulbs in your eraser bank. So instead of 10 glowing, you may only have 6, and it doesn't release all that metastability.
Question?
Yeah.
And is there ghosting or anything possible on DR?
On DR, yeah, actually there is, and it usually occurs at very, very low exposures, and it's almost an anomaly sometimes.
We had it yesterday.
Did you?
And me and Tech were really confused by it. 'Cause
Yeah,
my marker showed up in a place where it wasn't at. It was like, it must have been a.
Oh, really?
It must have been a ghost.
It showed up somewhere that you,
And you could see my marker on
Yeah.
film where I actually had it, and then you could see where it was from maybe an image earlier.
yeah.
And we had to repeat it because it was right in. It was
Right.
really weird.
And it, yeah.
And I told her I didn't know that could happen on DR.
Yeah, well, I didn't either until, I actually saw it one time, and there's no rhyme or reason for why it does it.
Yeah.
Because it does seem to happen at very low exposures. Was it outside of the collimated area?
Yes, it
Yeah.
was.
Yeah,
Yep.
so, but it doesn't happen every time, so, you can't predict it.
Yeah.
Whereas these, if the eraser bank is burned out, it has a tendency to do that, but, it's like everything else that's electronic, sooner or later, you're gonna have something that nobody can really figure out what happened there. Nobody's defined exactly how ghosting happens on DR yet, as far as I know. So on display, the resolution depends on pixel and matrix size. So what you want is small pixels and a big matrix, right? So you're looking at the dry erase boards over there. It's a big board, right? But how much resolution would you have if we were to try to create an image and the only thing that we could represent is 2 different small individual portions of an image on that board? In other words, we broke that up into 2 pixels. What would your resolution be?
Blurry, grainy.
Awful. You couldn't see anything. So what you need is a whole lot of little bitty pixels and a great big matrix, right? So you need little bitty pixels and a great big matrix is what you need. That will be your high resolution monitors. In addition to that, chapter 14, 15, 16 talk about bit depth. And bit depth is different than your matrix. Bit depth is essentially how many shades of gray you can demonstrate. So if you had a bit depth of 2, what you would have is the darkest possible image and the clearest possible image. So bit depth, it doubles, every time that they have a new monitor system come out. So bit depth of 4 would be, again, dark and light, and then you'd have 2 shades of gray in between, right? And then if you double that again, 8, you'd have 8 individual shades of gray. So that's something totally different. And your radiologist monitors are not only going to have smaller pixels and a higher matrix than what you're going to deal with, but they're also going to have a totally different bit depth. You're basically working off a computer monitor. So how much, anybody bought a computer monitor at Best Buy or anywhere recently?
Yeah,
How much was it?
like 140, 170.
Yeah, 140, 150 bucks, something like that. And it's probably bigger and better than this one, most likely.
144 hertz refresh rates.
Yeah,
It's
so,
really nice.
for our purposes, it's a great monitor, but compared to a radiologist monitor, those things up in the lab, not the TV, but the 2 things right next to the TV were something like $25,000 a piece. Yeah, so that's what the radiologists are dealing with, and those are, the high-end ones that they use really in the hospital. So those things are very, very pricey. They got an enormous bit depth, and they've got great resolution as well. So again, whenever you make yours look good, and then you send that to the radiologist, it might not look good, because you're comparing apples to oranges. You know, you've taken what looks good on a relatively low resolution monitor, and you send it to a doc that, you know, he's gonna be looking at something that's just digitally created, you know. So again, make sure that everything that you send to the radiologist is unprocessed. If you need to process, save the original, process another one, save it, send it both. But always send the doc the unprocessed image. That's not to say the unprocessed image in that, you know, the ones we're looking at that don't have the histogram applied to them, right? They don't need to see that. All right, so skipping over to chapter 16. We're not gonna spend a whole lot of time on this because I'm gonna do the whole chapter all by itself. But in our DR technologies, we've got three different possible DR plates, and the technologies are different between all three of them. You need to understand that they work a lot like, regardless of which one it is, they work a lot like a solar panel. And the way a solar panel works is you get sunlight on a solar panel, and it liberates electrons, and the electrons flow through a circuit, and then they can power your TV or your radio or whatever. So these really kind of work in the same way, but instead of sunlight, they're liberating electrons with X-rays. So the X-ray exposure on these liberates the electrons based on how much X-ray exposure they receive, right? So again, back to the ribs versus the lungs example. The lungs being easier to penetrate, they're going to receive more X-rays, so they're going to liberate more electrons that are eventually going to feed into the system to create a darker image than what you're going to see behind the ribs, all right? So how it occurs are a little bit different. So what you've got is indirect capture and direct capture. Indirect capture, what we've got are two different types. So we've got cesium iodide attached to a charge-coupled device. And we've got another one that is cesium iodide attached to amorphous silicone. And the reason we use the different elements that we use is basically the atomic number is high enough to create a lot of interactions with electrons. It's the same physics we've looked at since essentially day one of physics in your first semester. Electrons to knock out a shell in order to, you know, the higher the atomic number, the more electrons we can knock out of shells to create this, right? So a higher atomic number is what we're after there. The direct capture doesn't have the, like a charge coupled device, amorphous silicone. We're going to shoot directly into the phosphor, and it gives us, because we remove some of the steps, we're going to get the highest resolution out of them possible. So our direct capture gives us the highest resolution. Most of the time we've got a better bit depth as a result of just the interactions. Our contrast resolution is a whole lot better, as well as our spatial resolution is so much better as well. Now here's the rub. No matter which one of these we use, film still has a higher resolution than CR and DR. So why don't we still use film? Actually, it's pretty cheap. Well, yeah, the equipment's cheap, right? The films, eventually, you gotta store the films, that takes up a room in a hospital, so there's an enormous trade-off in cost that could be eventually more than the initial layout for DR.
Just efficiency.
Efficiency is what they sold us on.
Yeah.
You know, they said, oh yeah, you're gonna be able to cut your staff back by maybe half because, you know, it's just so much easier, you just shoot into it. But, you know, talk to Mindy about that. Who's at UT? Yeah, talk to Mindy about this. You know, because she said that now y'all gotta log into like 2 or 3 different systems in order to, so efficiency, that was a big selling point. It hadn't worked out that way. really, the contrast resolution is all about the contrast resolution. It's so much higher with CR and DR, especially DR, that we can overlook a little bit of a loss in sharpness resolution because the contrast resolution is just off the charts. You don't see a whole lot of compensating filters in clinicals anymore just because you don't need them. If you had anybody, back in the days of screens and films, if you had anybody with any kind of size whatsoever, you were looking at 2 views for a T-spine. You were looking at swimmers on absolutely everybody. You just, a foot, you had to shoot for where the pain was. If the pain was in the distal portion of the foot, you had to shoot with one technique. If it was in the arch of the foot, totally different technique. If it was in the heel, even still a different technique. With CR and really with DR, one technique gets it all. So, contrast resolution and the ability to make a diagnosis based on that contrast resolution is so much better with DR. So when we're talking about contrast resolution in the digital world, what we're talking about is dynamic range. Same thing. Okay, so it's the ability to distinguish anatomical structures of similar subject contrast. On screens of films, if you had a hard time seeing kidneys on KUB in your first semester, now with CR and really with DR, it would have been well into your second year before you could see those, on the film. Just totally different world. So without contrast, resolution is immaterial. You could have the perfect image recorded as far as sharpness of recorded detail goes, but if you can't see the difference between tissue types, it doesn't matter, right? So, but likewise, at the same time, your contrast resolution has to have some spatial resolution with it as well, but without contrast resolution, you can't see the spatial resolution. Okay, so CR, especially DR, has a very, very high dynamic range. So speed is something that y'all are not real familiar with, having to change screen speeds and things like that. We've talked about it a little bit, but speed is just a measure of the sensitivity of the image receptor system. The more sensitive it is, the higher the speed. So what we went from and to, just kind of walking through it. Par screen film was 100 speed film. And it's really film screen combination. So that is what they call par speed. I never worked with par speed. It was gone before I got into, even into school. So what we had in most cases was what they called high speed, which is 400 speed. So you have 100 speed up to 400 speed. 400 speed 4 times as fast as 100 speed. All right, so 100 speed to 400 speed, since 400 speed is 4 times as fast, that means that you could use 1/4 of the radiation to receive to create the same image, right? So it's all about radiation dose reduction. Remember that introduction of double emulsion film and screens, intensifying screens, was nothing but cutting back radiation exposure to the patient. So 100 speed image receptor is 100 times faster than direct exposure on a film, okay? So by introducing intensifying screens, it cut the patient dose back by 100 times. And then by increasing the 400 speed, it cut it back by another 4 times. So the efficiency of an image receptor system in converting X-rays to a signal that on the image receptor is what we're talking about, the speed. The increased speed means increased sensitivity, increased efficiency, which comes with a lower dose. What you're going to have a tendency to do on tests is going in the wrong direction, okay? So as speed goes up, your mass goes down. If you change from a 100 speed system, and usually when people make this mistake, they have the numbers right, but they have the direction wrong. Okay, so if you go from a 100 speed to a 200 speed, then what that gives you is twice the signal. So what do you do with your technique? You reduce your technique by a factor of 2. So if you go from 100 to 400, then you reduce your technique by a factor of 4. If your question says that you change from a 100 speed to a 400 speed system and you do nothing with your technique, what is that? Let's say you had a perfect image on the 100 speed, then what happens at the 400 speed?
You'll have high contrast.
Is that?
Wouldn't you have high contrast?
You wouldn't have too high contrast, what you would have is too high exposure.
Yeah.
Right. Okay, so pay attention to what the question is asking you. If you increase, and it's asking you for a change in technique, then you increase your screen speed, then you've got to reduce your technique.
It's confusing that it's called speed. Why is it called speed, not just sensitivity?
That's a good question.
That really confuses
Yeah.
me.
I don't know.
What is this speed? What are they actually measuring? The speed?
Right, well, it's speed of light, so it's
Yeah.
all, yeah. It's,
It always seems like it could just be called sensitivity, and that would make a lot more sense.
or efficiency.
Yeah, exactly.
You know, or glow, you
Yeah.
increase the glow, that would
Yeah,
say it all right there.
exactly.
So that's basically what we just talked about, is as speed increases, then we get twice as much exposure. 4 would be 4 times exposure. Okay, so, and also that's what we were just talking about. Test questions will require calculation of mass with changing image receptor speeds. So some questions may require calculations with image receptor technique, grid ratio, and all that, just like what we had in the map test and stuff. So that's not going away. Really recommend that you kind of dust off those notes and look back over those. It's not going to dominate, but there's going to be questions about it. Okay, so CR systems, whenever we changed from film to CR systems, we lost some speed. They were equivalent to a 200 speed system, so what we saw was an increase in patient dose. So the other selling point of CR system was, not only were we going to increase efficiency, which never happened, but they said that our patient dose was going to decrease. And what they were talking about is not individual patient dose, okay, for individual exposures. What they were saying really was your overall global dose is probably going to decrease because minor differences or minor mistakes that you're going to make in technique aren't going to be an issue because of post-processing, right? So our repeat should go down, so overall the chances for a decrease in radiation dose existed. But the initial dose jumped by a factor of 2, okay? So very important distinction to make there. So what they did is that since KVP doesn't really affect contrast the way it used to with screens and films, instead of increasing our mass, which would effectively double the patient dose, what we did was increase KVP, okay? So since CR system is 200 speed relative, which is half as fast as 400 speed, right? And we want to increase our exposure just using KVP, what could we do?
Say that one more time.
What's that?
Say that one more time.
I don't think I can. Okay, so we lost speed, right? So we went from a 400 speed system to 200 speed system, which means our exposure was exactly half of what it needed to be. So how could we make that adjustment just using KVP?
Increase?
Okay, increase, but by how much? Double KVP?
15%.
Yeah, that'd be double mass, 15%, right. So what we did was whenever we went to CR, we increased KVP by 15%. Okay? So now we reintroduced that exposure that we lost. We didn't really lose exposure, we lost detection, essentially, right? So by increasing KVP, that went away. Did the patient dose go up? Absolutely it did, because if you increase KVP and you don't reduce mass, then your patient dose goes up, but does it double? And the answer is no, because you get more penetration to the patient. Now introduce DR systems, which are just as fast as screen and film. So we went from 400 speed to 200 speed,
Back to 400.
and we went back to 400 speed, but does KVP affect contrast the way it did in screens and films? No. So what do we reduce going to DR?
You're reducing
Exposure, patient exposure.
Well, patient, yeah, you can reduce patient exposure by doing what?
Lowering our KVP.
We lower the KVP, it is, we'd reduce the exposure by reducing KVP. But since KVP is already high and our dose didn't double,
You reduce your mass.
reduced mass, right? So we cut our mass in half. Now we've got the higher KVP, which led to a lower dose with the same, relative exposure in mass. So truly, once we got to DR, our patient dose went down. It just took a while to get there. CR made it go up, and then with the hopes that with a reduced repeat rate, that it would go down as a population. But once we got to DR, and I really think this is why, part of the reason why Medicare and Medicaid are really putting their foot down on conversion to DR. A lot of your hospitals aren't getting compensated, or getting the threat of not being compensated unless they go to DR.
So the DR forced to reduce mass, right?
Yeah, we could have reduced KVP and dose would have gone down, but the reduction of dose was more significant by reducing mass.
Yeah, because you'll have lesser time under radiation.
Right. The downside to all of this is the faster the image receptor system that you have, and the less mass you need, what might you introduce?
Model?
Quantum model, there you go. So by going from screens and films to CR, we didn't really have a problem with quantum model, right? We had the same mass, now we just needed to increase in KVP. By going to DR, unfortunately, the possibility of introducing quantum model by reducing our mass now, introduces the chance of quantum model with DR systems, because they're high speed, plus we use the higher KVP. So there's your quantum model. It's just that speckly appearance that you see from lack of photons. So quantum, number, model, speckly, quantum model. It's a speckly appearance because you don't have enough numbers. And that's what it looks like. That's just because of low signal. Could be because of high KVP. Even in a lower speed system, if you increase KVP to a point where you've reduced mass to a point where you don't have enough mass, you can introduce quantum model, even on a lower speed system. But it occurs worse, or more often, on high image receptor speeds, and especially thin anatomy. You shoot hands on a high speed image receptor at, 90 kVp, you're gonna have a lot of quantum model. Alright, so regardless of what image capture we have, okay. We'll talk about this, and then we're gonna have to break it off here pretty quick. So contrast and density, regardless of what type of image receptor system we have, the physics of the interaction inside of the patient, as we describe it, is still what we think happens inside of the patient. You know, we're talking about photons traveling at speed of light, bouncing around inside of the patient. It's theoretical. But the best explanation we have is still what we understand or think we understand about photoelectric interaction inside of the patient, transmission of scatter radiation, right? So all of that has been unchanged regardless of what image receptor speeds and detection and dynamic range is done. We still have to have that differential absorption inside of the patient. So we still have to have patient contrast so that we can have differences in intensities coming through the patient so that we can record those on the image receptors. So in our contrast and density in the beam, what we're controlling is the quantity and quality of the radiation striking the image receptor, and two things are going to control that. If your KVP gets high enough that you penetrate all tissues with the same intensity, basically, you're shooting hands at 130 kVp. Everything's going through the patient. You're going to lose contrast. In a normal range of KVPs, we've seen it already in the experiments. There's just, there's sometimes just not a whole lot of a difference, right? So you can take your KVP to an illogical extreme and you can actually see some differences. And at the same time, if your quantity controlled by mass gets so high that you completely flood your image receptor and you wash everything out, then also you're going to lose contrast. So you can lose contrast with both KVP and mass. It's just a matter of how you get to it. So going back to the H&D curve, we've talked about the H&D curve. If you get into the shoulder or the toe portion of the H&D curve with your mass, everything's so dark you can't see it. Everything's so light you can't see the difference in tissue types. Then mass, with mass you can lose some contrast as well as KVP. So it's controlled in the reader by the histogram. Your histogram, the difference between histogram and lookup table is subtle. The lookup table is the stored histogram. That's what's inside of the computer that you're telling the computer that you want every hand to look like this particular histogram. That's your histogram, or your lookup table. Okay? Your histogram is what you shoot. So your histogram is going to change for every patient. You make an exposure, you get a histogram. It's a range of exposures that you actually made in densities that are represented. So how these things work is there are some pictures of histograms in the book, and what they are is just this graph with all these lines with different peaks and valleys. So, kind of taking that out to just looking like 5 different levels of density. If your histogram that's saved into the computer, you say, okay, I want these range of densities. I want every hand I make to look like these range of densities. And you make an exposure, let's say, with too low of a KVP, and you got too high of a contrast. The computer takes your histogram and it applies it to the lookup table and it says, I want this to look like that. They look similar, right? You can tell they're both hands, but what's going to happen is it's going to basically superimpose them so that they look almost identical. Okay? So both of them are histograms. It's just that the lookup table is your stored histogram. And when you get to window with leveling, that's where you pose the process and you tweak it a little bit and you make the contrast look a little bit different. So window with leveling is your contrast and density. It's your brightness and your contrast controls on your computer or whatever. That's just window and leveling is all it is. So
when you change from auto to fixed, you're taking the lookup table off?
yeah,
Okay.
yep.
So
that's
it's the
exactly
lookup,
what
you're not taking the histogram off,
No.
you're taking the lookup table.
You've still
Okay.
got a histogram,
Okay.
but you're taking a lookup table off. So
Okay.
when you make your exposure and you get that unprocessed image, that's what it's doing.
Okay.
And that process of processing it is what you call automatic rescaling.
Okay.
So you make your exposure, And it's hiding that. It says, okay, this is what you shot. This is a disaster you made of your image, right? We're gonna make it look like that,
Okay.
right? So that process is your automatic rescan.